Yes. Dat is mijn telefoon.
Yeah, now it's up to me for the Fourier-Based near-field acoustic holography. Thanks to Ines, I think half of my presentation can be skipped, which is good concerning the time. I think some of you were present at Munich where I did a presentation on Sorama and outreach. I will now dive a little bit deeper into the technology behind it. My name is Rick. I'm founder and director of Sorama. It's a spin-off of the TU Eindhoven. I did my PhD with Ines as my guide. Tomorrow you will be visiting also Sorama at the Strijd S complex, and I will tell you a little bit about entrepreneurship then. So I will skip that also now and continue with near-field acoustic holography, planar near-field acoustic holography in this case, with a Fourier-based method. To start with, I will show you an example. I think some of you might have seen it already, but it gives you a nice insight in what you can do with inverse acoustics, with near-field acoustic holography. This was a case at Philips quite some years ago. There was a smartphone screen, touchscreen, that had a 13 kilohertz beep, and while you put it on the table you didn't hear anything, but when you kept it to your ears you would hear the 13 kilohertz beep quite loud. And the question was, where does this beep come from? And the second part is, it needs to go out before we put it into production. At Philips there were about, I think, 12 people in a project group working on it for 6 months to try to find it. They used a laser vibrometer, they made a whole model out of it, they did all kinds of testing in acoustic rooms. A lot of trial and error, couldn't find it. What we did is we placed it on a scanning system with MEMS microphones. I have a small version of it over here. This one has got 16 microphones. Currently we have our standard array, like Ines also told you just now. We have a standard array with 1024 microphones. But I will pass it along, you can take a look at it. It's actually a printed circuit board with openings in it. And the gray parts on it, the boxes, are small microphones, and they're also used in your iPhone. And we did a scanning measurement at hologram distance, so at a distance from the source, and we calculated back with planar near-field acoustic holography onto the source surface. And then we got this image at the source surface. It wasn't the screen itself that was making the noise. We found it out quite quickly. We turned it around and we took a look at the flexible printed circuit board that was actually controlling the smartphone screen. What you see here is the sound pressure on the source surface, so back calculated, so the inverse solution was determined, and we see red areas with high acoustic pressure and blue areas with low pressure. Looks a bit like a thermal camera, and through it you see the objects as well. But from this you can only see where the areas are where most sound is radiated from. But we don't have a clue yet which component it is. It might be this chip or some other parts of it. But the nice thing is, because we can make an inverse solution and we have measured pressure, amplitude and phase on all those few hundreds to thousands of positions, and we can calculate that back and also restore that information and make a video, actually a number of sound images over time within the phase of 13 kilohertz. So looking at this is a sound video, a high-speed sound video. So it's this specific case is about 50,000 times delayed with respect to real time. And now you can see the red parts are the high pressure areas and the blue parts are the low pressure areas. And you can, well, we weren't allowed to talk about water in comparison with acoustics, but these videos, they tend to look a bit like water behaving like throwing a stone in a pond. And we see that the actual vibrational source is over here. And the wave is moving through the flexible printed circuit board. Of course, this part of the bending wave is actually exciting the air particles and can be heard as the source itself, but the vibrational source is over here. It's like the excitation on the flexible printed circuit board. This one was moved out, all problem gone. It's another type of capacitor. Well, I can skip this now because Ines already told. We are looking actually at two parts of the acoustic field in the near field. It's the propagating part and the evanescent part. And we are observing with, in this case, the crosses are the microphones, the observers. If you only look at the far field part, you don't have the evanescent part of the sound field. But spatially speaking, there's a lot more information in the evanescent part. And compared to near field acoustic holography, of course, I also have the far field technologies, like beamforming, where only the phase of the incident wave is actually back calculated. And you can see here that the resolution is much smaller than the high resolution of the near field images. The resolution here is determined by the wavelength in air. And over here in the Fourier acoustics, the resolution is determined primarily by the positioning of the microphones, so the spatial sampling frequency. It's going around, but the nice thing is with doing the measurements, apart from the algorithms that you use, is that you also need to have the sensors. And what's nice right now is that with Fourier acoustics you are back calculating from a certain plane or cylinder to another plane. And in that case, by using Fourier acoustics, it's nice to have a lot of sensors. So you know a lot of spatial positions, you know the acoustic pressure, and you can then back calculate towards a very high resolution image. And of course, when you use the classical measurement microphones like B&K, you spend like 1,500 euros per channel. If you would build such an array, which is a 1024 channel array, you can do the math. And the nice thing is that in 2008, the MEMS microphone with a digital output was introduced at a conference. And in a wafer production process, actually it's a MEMS microphone. You have the mechanical part of the microphone integrated with the ASIC, with the analog to digital converter, and also kinds of other electronics. So this is a really effective way to measure many points in the acoustic field at once. And this is another example what we can do with it. Actually, we recently designed a 4096 channel array, and you can do these kinds of. Here you see the arrays. Oh. It's actually here in the lab. Are we going tomorrow? Are we going to that lab or not to the automotive lab? That's in the automotive lab, just around the corner here. And here you can see that by having all those measurement positions sampled at once, you can get huge sound images and a whole overview of the responses of your system, also over time. And these are all made by Fourier near-field acoustic holography. Other parts, what you can do with them is, this is a scanning of 4 of those large arrays by 2. And we imaged at a very low frequency of 72 Hertz. And you can still see quite some nice details. And you can see the modal deflections in the door, in this case. And if you look at some other frequencies here, you see some kind of mode in the wheel itself, turning around with the velocity of the wheel. And I will just skip through it. And here the thing is, you're measuring at some few tens of centimeters and then calculating back. So you have a slice, a plane slice, in front of your source. So not with the inverse boundary element method where you can map on the surface itself, but we're taking a look in this slice in air. You also see, in that slice, you also see parts of the waves moving away in the plane itself. And this is on a very high frequency. You can even see it's an in-wheel electric motor. You can even see the poles of the magnet. Well, and of course, when you have all that information and you calculate back towards the source, you also know indefinite amount of parallel planes up to the source surface where you can also calculate acoustic pressure. But because you have the gradient of the acoustic pressure, you can also determine the particle velocity and the sound intensity. And this is just a shot from our user interface, where you can see that based on just one holographic measurement, one array measurement, you can have all these insights up to that plane touching the source surface. So you need to keep some boundary conditions into account. But you can see how easy it is to dive through the whole acoustic field. Well, I was talking about those boundary conditions. And in Fourier acoustics, because I'm now showing the planar solution, you are measuring with your array at a certain distance, and you have a plane full of pressure information. We call it a hologram. In Greek it's holos gramma, meaning whole message. So you're actually catching the whole message that you can find with your array, and you calculate it back towards the source surface. But the boundary condition is that you have a source surface behind which any kind of source distribution is possible. But on the other hand, you need to have a source-free half space without any sources. What you can do there is a solution for this problem. Ines already mentioned, but showing it again. When we actually have the hologram information, we want to find the pressure at the source back. You can do that with Rayleigh's convolution integral. And what's nice is that this is quite hard to calculate on your computer, but what's very nice is when you do a Fourier transformation of your source, and here you are making a solution for the not the inverse problem, but the propagation of the problem. When you do a Fourier transformation, so the same with time frequency transformation, we now do a Fourier transformation over the x and y axis, so a 2D spatial Fourier transformation. And the nice thing is that a convolution integral, a 2D convolution integral in the wave number domain, which is the Fourier transformed spatial domain, is simply a multiplication with your propagator, with your inverse kernel. And as such, you can also go the other way around. You have the hologram information in the X space. You make a Fourier transformation towards the wave number domain, and because you know the boundary conditions and you know the propagator, you can determine the pressure in the k-space, in the wave number domain, on the source surface. And by just simply going back with an inverse Fourier transformation, you get the spatial information at the source. Well, that sounds quite simple. Here you see an example on a hard disk drive. Here we are using independent microphones. You can also do it scanning, but then you need a reference microphone to reference the phase information along your measurement. And you are filling up your matrix with pressure measurements. This is what Ines already showed. Every position, every pixel in the image is a measurement by a microphone. So I don't need to explain everything over here. Like Ines also said, on every signal single frequency bin, there's other holograms available, so other measurement data. And you see that here also that the holograms differ from each other. Of course, there's a different physical behavior behind it. And when you then also look at the differences between what you can see on your hologram plane, it's very much different from what's actually happening at the source. Here you see that spatially it's much more bulky, it's much more, the higher spatial information is out of these pictures. But when you calculate back over 6 centimeters, you see that here you have a 1-2 mode of the disks turning around. And here you can also see that a lot more spatial information is available. And here you could identify this source image as being a point source over here at the axis. But when you calculate back, you see actually that it's modal deflection in the plate, in the surface of the hard disk drive, that's causing this kind of radiation. So also from an engineering perspective, it's very important to calculate back onto the source surface to know what's really happening vibrational-wise, in order to be able to solve it most effectively. Here you have the difference again between beamforming and near-field acoustic holography. What's nice there, that beamforming can never cross this line here, resolution-wise. So, given a certain frequency, over here you have 10 kilohertz going down to like 10 hertz. You see that the resolution in meters is it just goes down with the frequency. Like at 100 hertz in air, it's like 3.4 meters wavelength. You cannot cross that resolution limit for the beamform. You have some ways to do some signal processing to find the center part of it, but really the physical resolution cannot be beaten. But when you go with near-field acoustic holography, given a certain distance or a spatial sampling frequency, you can beat that resolution limit whenever you want, just depending on your measurement set. Now the nice thing is, given the boundary conditions, and I have some new videos showing what the near field is doing with infinite plate and bending modes. What's very nice to see is that when you have the wave equation, and it's quite a simple model, and you have the plate exciting the air particles. Here you see every point is an air particle. You can follow a single air particle very close to the surface, to the source, and also follow it in the far field. And you can see in this case, where we have a bending wave that's actually below the coincidence frequency, you see that we have a propagating wave. And when we are very close to the source, and here it's nice in this image is that you can really follow the air particle and what it's doing. So it's not bound to transfer its energy to the next air particle and as such propagate away from the source. But what it's actually doing is it's just turning circles. And here you can also see that the energy is being dissipated between the air particles that are more or less next to each other. So here you can see the acoustic shortcut happening. And when you are looking at the same air particle, like in the far field, you see that it's hardly moving. Hardly any pressure variations are happening there. I also used the example with the bath, so I won't tell it again. You still know it from Ines. What's important for Fourier near-field acoustic holography is that with the microphones you take a rectangular grid most often, because you can then use the fast Fourier transform in 2D. So that makes it a very fast method. Actually, it's one of the single fastest methods for near-field acoustic holography. And that makes it that you can more or less do it real time with the arrays that we have right now. But an important step is there that you need to do spatial sampling. So really the positioning in open space of your microphones, which is on a rectangular grid in this case. You need to do the pre-Fourier data handling. Like when you are sampling in the time domain and you want to do a frequency transfer, you need to do windowing to not have any leakage into the frequency domain. Well, actually the same holds for the spatial frequency domain. Also there you need to take care of that you don't get any leakage into the wave number domain, because leakage in the wave number domain will give you a bad reconstruction. So you have the next step is the Fourier transformation. You have the inverse calculation, where simply the inverse propagator is multiplied by the pressure on the measurement surface, and you upgrade the exponential decaying parts, you upgrade them up the exponential again. And here you have the regularization, as Ines already mentioned. If you don't do that, you blow up noise. And following that, you inverse Fourier transform again back to the spatial domain. And then you get this result. Here you see the half space again with sources and the other source-free area. Another good example of evanescent waves is you have, I think tomorrow you will also be able to play with that a little bit. If you have a tuning fork and you hit it on the table and you hold it in open air and you have an A, for example, 440 Hertz, you won't hear it. But when you place it on the table or on a wooden plate in this case, and you transfer the energy into the eigenfrequency or close to it of the plate, you get structurally larger wavelengths, and these tend to propagate outward, like Ines already also explained, and then you can hear it, and then you can hear the 430 Hertz, 40 Hertz. Well, I also use these videos still, but what's nice to mention is that these propagating waves in the wave number domain, so in the Fourier transformed domain where we have the wave number in x direction and the wave number in y direction, here's the middle, so the DC component. Here you have the coincidence frequency, which Ines also explained. Within that circle in the Fourier domain, it's all propagating waves. So they all comply to this kind of behavior. And when you get outside of this circle, you get the evanescent waves. The further you get outside of this circle, the more the waves die out. So you could say that by measuring the distance, at the hologram distance, your image, if you take an image there from the array, you won't see any spatially high intense movements, but the information is present. Only the level is much lower in the Fourier transform domain than the propagating waves. So if you transfer that into the spatial domain, you will see the most gradual sources, the propagating part you will see. But when you move back with near-field acoustic holography, you see that actually superimposed on those propagating waves is the much higher spatial information. And when you construct nicely back to the source, you see that there's a lot of information present. I was talking about sampling, and Ines also told that by using just 5 microphones, you get 5 points of information. Let's just say that we are measuring at the hologram distance, and we would be looking at this propagating wave. Also, the Nyquist criterion says that we can observe this propagating wave. But as I just mentioned, superimposed on this propagating wave is the much higher wave number of this kind of source. And when you place the measurement positions, the sample positions, on these variations, you can see that you cannot find all the specific details back by just observing those 5 points. Of course, from time frequency analysis, you have aliasing, just when your sample frequency is not high enough. Same holds for the spatial domain. So you more or less have spatial aliasing, undersampling of the information that is present. As such, you cannot reconstruct it at the right resolution, but you might even miss the correct vibrational pattern. So it's very important to know what you're doing when you're measuring with microphones in the near field. That's the message. Well, if you are just looking at the sound field from, you would like to have a measurement array that's indefinite and with as much microphones as would be possible to get the best resolution, but we are actually discretizing a lot. We bound the aperture that we're looking at, although we have an array with 1024 points. But we are also discretizing in the positioning, in the resolution that we can determine. When you do that, you get a discrete Fourier transform, and if you don't handle that correctly, you can get the leakage and you can get the problems that I already mentioned before. So let's say the complete source looks like this on the source surface, but we can only observe just a small part of the source, of the measurement. Before, like 10 years ago, 15 years ago, what we did in planar near-field acoustic holography is place a spatial window, like a Henning window or a Taki window, over your measurement data. And when you place a Henning window over it, you just push away half of your information, especially on the sides. You cannot distinguish what the exact source is anymore. So you can see that here. This is actually the information that we want to know, but you only get information in the center. But what's nice, what we have developed is actually based on the original aperture. We made a model out of it with a Berg extrapolation. And step by step it goes like this. So we have the original information with every square is a microphone position. And based on the models that we have here for the spatial vibrations, we determine a next step outward. We determine what could have been the acoustic field outside it. And we do that for both directions. And we sort of get one part is the real measured field, and the rest is a virtual array, a virtual measurement. But the nice thing is, for Fourier transformation, we can now put the spatial window over it. All the information that we measured is still intact, and we are able to do a good back calculation into the Fourier domain. So when you look at it at a measurement distance of, for example, 2 point sources, you get this information at your measurement, which you can hardly distinguish both sources. And you can see that in the wave number domain, where you have the zero crossing or the center over here, you see that there's only propagating parts still present, And when we take steps closer to the source, you can see that at the higher wave numbers, so further away from the center, more information, more energy is being present. And when we back calculate for measurement to source, and then go back to the spatial domain, you can see how much spatial information you can reconstruct. But that's in the actually in the case where there's no measurement noise or no noise available. And these are the steps. So you have the inverse propagating, low pass filter, the regularization. I will show you that in a minute. And then the back calculation. What's nice is that in the inverse propagator here is just a multiplication, and you can use any kind of kernels to be able to find pressure from velocity in any kind of direction, sound intensity. But you can also use velocity sensors like a microflone to be able to back calculate the sound pressure. And this list or this matrix gives you a very easy way to find all this information. And the first example that I gave, I just showed the sound pressure field, absolute sound pressure field with the sound pressure over time. But from the same measurement, you can also get the absolute particle velocity out of plane. And you can see here already that the out of plane vibrations, so the real particle velocity, is much more centered around a few spots on the printed circuit board. And here you see a moving image again. This looks a lot like the images that you get from a laser vibrometer when you are testing all the out-of-plane velocities. But the nice thing is you can actually solve this problem by going from sound pressure, particle velocity, and sound intensity, where you can really see what's actively being radiated. But you can also go from absolute sound pressure to the sound pressure over time to more or less get an insight into how the vibration works. You can solve it through both ways, because here you can see that the piezoelectric capacitor comes out easily. So that's nice. So you have one hologram with sound pressures, and you can determine any kind of information up to the source surface that you like. An important part is the regularization. When you have the measurement and you do a 2D Fourier transformation, so here's the zero again, DC component, any given source, it doesn't really matter, this is some bending waves, you can see that only the propagating information is still intact. Here you have the coincidence frequency, the radiation circle as we also call it. And you see that the outside field, the higher wave numbers, are gone. But when you your inverse propagator looks like this. So you can see here, the more you go outside, the higher the wave number, the stronger the multiplication factor is. And what happens here, if we just take a look at the kx axis, you can see here that given the amplitude variation that we take, the propagating part is not being amplified, but you see the further we get outside the radiation circle, which is here, the coincidence frequency, the higher the wave number is, the more the wave gets amplified towards the source. But if you look at it, if you would filter this with a low-pass filter, you would see that actually the resulting line goes like this. So this part won't be reconstructed carefully. But if there's noise around, and the noise is stronger than the information that you want to retrieve, then not using the filter might blow up your solution. So when you don't regularize it, you see that the propagator, the inverse propagator, makes it so that all the noise that is around in the higher wave numbers gets blown up. And a regularized solution will give you the good solution. When we look at the hard disk again, it might look a bit like this. So here you see the low pass filter. So the more I open it up, the more wave numbers I let in. But you can also see at some point the measurement noise takes over and your correct solution is gone. This was, so you see here again. Here you are over-regularizing, so a lot of information of the source is being thrown away. Here you have the optimal solution, and now slowly noise is being blown up at the higher wave. And the L curve, which Ines also mentioned, is a way to actually determine which kind of cutoff you need to take to have a good balance between information of your source and not blowing up the noise. So these are the steps which I've shown you. The spatial sampling is very important for Fourier-Based near-field acoustic holography because of spatial aliasing problems, leakage. When you have conquered that, you can have a very easy inverse solution of your problem. But you need to regularize it carefully to not get garbage out. And finally, you can do the inverse Fourier transformation. And the part which we actually added with the extrapolation is being cut off again when we are in the spatial loop. Okay. And just to give you an overview of what you can then do with near-field acoustic holography, of course you can do the sound source identification and the localization of the sources. You have the behavior over time and space. You have 3D propagation, so you can take a look at your field in any direction that you want. And just from having one acoustic hologram, so one pressure measurement or particle velocity measurement, you can get all your information in 3D, given that you have complied to the boundary conditions. And the nice thing is, especially the Fourier acoustics, you can very easily scale it up just by scaling up your measurement array, or if you have a large structure, you can increase the distance between neighboring microphones, but then you also need to get a larger distance to your source so you don't get any spatial aliasing. But you can go as small as those small devices. Like I said, in that part we don't use the B&K microphones, but we use the MEMS microphones, so we get a lot of positioning, a lot of sensor points in a certain area. And this is the product that we actually have on the market right now. You have the 1024 channel array and an online system where you can do the measurements and calculations. Also for far field technology, but the core is the near field acoustic holography. And our customers use it in an engineering process where they are cycling through, trying to know what their, in this case it's the MEA central heating system. They are trying to find out what they want to achieve actually by reducing the noise. They want to get an insight into what's happening and do their analysis and find solutions for the specific things that they found in the images. And you can close the cycle there in your engineering process. Yeah, we also, in August last year, we broke the Guinness World Record for largest microphone array. Actually, it was held by MIT with 1020 microphones. So our standard system has already 4 more. But in my team, we decided that beating it by 4 microphones would be a little bit lame. So we did it times 4. And here you can see that with the 4096 channel array, we're doing near-field acoustic holography, but also beamforming. And of course, you can also easily do directional listening with it. Here you see the beamformer. Nice IKEA closet with some sources in it, and you can just go around in the frequency domain. Here the whole system is vibrating, but when you take a look with near-field acoustic holography, you can see that you can really, of course this is slowed down, but you can really look at the dynamics of the system. And one nice thing that we found out, at a certain frequency, you get these kind of modes in the closet. And here is the same frequency with beamforming. And you can nicely see that a lot more insight is being given by using this kind of, using also the near field part of your sound field. It's got a lot of spatial information that can tell you things about how your source is behaving. Yeah, and in that sense, here you see a lot of different videos of different sources, but you can go ventilation systems, large generators, heating systems, but also plate modes, yeah, you name it. We actually say if it makes noise, we can image it. And an important part in the process is to be able to observe, try to find out, gain the insight into what's happening, physically speaking, build up an understanding, and as such move towards the sound design. Thank you very much. I don't know if there's any questions.
When you were saying about this section, that we can go as far as the first section touching the sound source.
Mm-hmm.
And then when you guys about, yeah, when we're talking about a surface, a 3D surface that could do all this, have you thought about putting your microphones on a flexible thing, or could this be something, or you have to just move your array all around?
Well, actually, it's nice that you mentioned it. This design, we also have it with a complete flex rigid. Yeah, you can bend it any way you like. But that's something that we have developed the prototypes of it. So you can also put it on a frame which you can scale. And we have already put it also on a cylinder, so you can go into an MRI or things like that. And as such, you can also easily do cylindrical near-field acoustic holography, or spherical, or maybe even combine all those methods. But the thing is that with the Fourier near-field acoustic holography, you would like some standard structures where you can have the easy multiplication to calculate back. Yeah. But indeed, we right now have hardware that's fully flexible, but which you can also scale up, because this is very easy to produce. So an array like you saw with the 1024 microphones, actually it's available for 12K, for 12,000 euros. 1024 channels, including data acquisition. So we're really breaking through also the barrier of having too expensive measurement hardware. And the flexible arrays can also be produced in the same manner. They're a little bit more expensive, but you have much more flexibility with making an array. Yeah. There was a question over there.
Actually, it was also repeated the wrong surface and also concerning that. So here it's, the medium is thrust between the source and the plane.
Mm-hmm.
So I think for Eindhoven there's already some solutions to take into account some flow effects.
Mm-hmm.
Is it something that can be also so? Is it something that can be developed for this kind of Fourier-based MA?
Yeah. So what was the first part exactly?
For the inverse acoustic method with like Eindhoven,
Yeah.
you can take this into account in some way.
Mm-hmm. Yeah, I think if you want to do that with Fourier-based technology, you Yeah, I think it's a little bit hard, but you have to determine standard parts of. So I think you can do some easier modeling on your surface. So have part spherical, part planar, and combine all those surfaces. So your source still fits in it. It's the same with the equivalent source method, where you also take some parts, and I think that would be a possibility for Fourier acoustics as well. But yeah, at the moment, at least we are busy doing the commercial stuff, and it might be a very interesting direction to do some research on. We are, at the moment, we are also, as a company, we are doing a lot of research, but it's primarily on the regularization part. That's really a holy grail to find the correct solution.
So these L curves are actually like really top secret. So this is the thing that's...
The L curve is not top secret, but there are some ways to... You know, the thing is how to automatically determine which is the best cutoff for your filter. But also, why would you only take a low-pass filter? Maybe you can take a filter that fits your source information perfectly and rules out a maximum amount of noise. But then the thing is, I'm looking for the source, and I don't know the source, else I wasn't looking for it. And if you know the source, you can get a perfect filter. So that's always your problem.
Any other questions? Okay, then, yes, I want to say something, then you may say something. So, about tomorrow.